Right, good morning. So we'll be quickly learning about lasers. It is 3.5 hour lecture actually, but we'll try to compress the important things in next 30 to 40 minutes. Right. So lasers is very easy. All you need to know is the acronym only. If you can understand what does it mean, each word if you can understand, it is done. So each word, let us see. You know that what is L stands for? Yes. So it is talking about the light, but it is not the ordinary light. Okay. Light you are amplifying. Okay. Amplification. So ordinary light will be taken and it will be amplified. That's why it is different to the normal light. So you will be studying about what are the peculiar properties of the laser compared to the ordinary light. There are some different properties. How do you get the amplification? It is very key point. You can get it by the process called stimulated emission of radiation. Is nothing but basically light only. No, you are taking light radiation only. Stimulated emission of radiation. So what is important here is for us, you're taking a light, then this light radiation and this radiation same. Basically there are different kinds of radiation. X-ray is also a radiation, microwave is also radiation, light is also electromagnetic radiation. So in these lasers we are not taking any other radiation. But why this name came is because before laser they could amplify something else, that is microwaves. They amplified microwaves, okay, not the light. Microwave is also radiation, so they say maser, M-A-S-E-R, maser, right? So Einstein thought something. He is also again a forefather, for this concept. But theoretically it is there, radiation can be amplified, but experimentally we did not observe until first in 1964 or somewhere. Microwaves are amplified through this process that is called maser. After that, why not light? Why only microwaves? Okay, so that thought came. Then we started the laser and amplified it. That's how we got first ruby laser very recently, maybe 40 years back only. Okay, so then we call it is now laser. So before laser what is there? Maser, M-A. M stands for microwave, remember that. Okay, so now each term if you understand, chapter is done. Okay, so now let me start with how do we produce laser. We'll go from known to unknown. Okay, so what we know is production of light production. Somebody tell me, how do we produce light? Electrical light or candle light, or by using the rocks you are producing the light, any form of the light, usually whatever you know. How do we produce light? Ma? In the form of photons light is coming. How it is coming? Whatever you know, tell. Yeah, light source, what is happening? What do you mean by that?
Only single photons traveling.
Yeah, that is what is textbook knowledge, whatever you read. Suppose I take some incandescent bulb and I switch on the power, light glows. What is happening? In simple words, you tell what is happening. Electrical energy is passing to the tungsten filament. Then, so the heating. So heat is giving light. Is it what you are understanding? Okay, let us look into it. How general light is produced, then how we can amplify, what is stimulation emission, we can finish, then we'll go. Okay, so that is half true, but generally what is happening is for the light production, quickly I will tell, then I will recap. What happens is we have atoms, Okay, everywhere you are taking some tungsten filament or something, what you know is atom is having like this nucleus, and around it energy levels are there where your electrons are revolving around these energy levels. Energy electrons can be 1 or 2, depends on your atomic numbers, right? So this electron, suppose you focus on any electron, suppose I take this electron revolves only in this particular shell because its energy is only that much. Suppose it has some energy, let me call, because this is E1, let me call it is E2. This electron E2 having the energy E2, and it is revolving there only as long as in that shell its angular momentum is conserved. That's what Bohr said, right? So it is safe and stable there. Now nothing happens as long as it is doing like that. So now what I did is, you are switching on the electrical energy, the switch. So it energy you are pumping to the system, to the tungsten. Okay? In the tungsten, such kind of atoms are there, electrons are there. Now they are happily revolving. Suddenly some energy came to them. Okay? So suppose you supplied some energy to this guy. You supplied. So as long since it sees the energy, now it fills up. The energy is E2. Additionally, some energy came. Suppose let us call it is H nu for simplicity. It can be some E, though it is not photon, call it is H nu. So now its energy is E2 plus H nu. Taking that energy, it goes to higher energy level, somewhere E3 it goes, but it cannot stay there permanently because it is not stable state. Then it has to eventually come down to its original position. But while it is coming, whatever extra it has taken, it should give back. So the giving back can happen in two ways, either in the form of light or in the form of heat. Okay. If it gives in the form of light, the light comes out. If it gives in the form of heat, it will heat the environment. Okay. That is the simple process happens. Okay. It takes the energy, goes to excited state, comes down. While coming down, it releases the energy that in the form of light. This process is clear. All right. So now if it is clear, what we do is we will extend the same discussion in different manner. So basically what is happening, energy is coming, it is absorbing the energy. Keep it in mind, absorbing the energy and going to excited state. Okay. So it is absorbing, which means somebody is forcing this guy to go. It is not natural. Okay. Somebody is forcing, or else we say somebody is stimulating. Stimulating is nothing but forcing. Okay. So we say the absorption is it natural or stimulated? Natural means spontaneous. Stimulated means forceful. So is it spontaneous or stimulated? So whenever you talk about the absorption, it is stimulated absorption. So the first question they can ask, explain about the stimulated absorption. Okay. Stimulated absorption. So what is stimulated absorption? Let us see. Stimulated absorption is nothing but easy. I have atom having the ground state. Now I am not representing like this energies. It is another way of representing. I am putting two energy levels. It is my ground state. For simplicity, I am taking only one electron. This electron is sitting there. When I say the ground state, let us see the ground state energy is E1. Right? Now I also have so many energy levels top of it. I take only one such, that is called E2, but I have E3, E4 like that, so many are there. Okay. Now this energy of this electron is only one, so it stays there. But if you want to take this to there, to up, you need to supply the energy, right? So let us supply some energy externally. The term externally is important. Supply the energy externally. Okay? From outside does not belongs to me, to the system. Supply externally. When you supply externally, it will absorb the energy. Then it should go to E2. But look, wait a minute. This is important. You want to go from E1 to E2, you cannot go on yourself. You need somebody help. Some energy you want. How much you want to go there? It is like asking, I want to go to Delhi from here. I don't have money, but the cost to the Delhi flight is something 4,000. Okay. Now, if you give 1,000, can I go? I cannot. You need to match the difference. Hello? Yes, no? Only if you can give 4,000, then only I can go. Otherwise, I cannot go. So, the difference should be matched. That is very important. So, the H in U should be equal to what? The difference in the energies. Then only this happens. Look, in between it is forbidden. It cannot go because 100 only given or 1,000 only given. Let me go here. No, it's not possible. It cannot go here. It cannot go here. In between, there is no energy state existed for the electron, that we say it is forbidden state. Valency band, conduction band, forbidden. It cannot either stay there, either be here. So you must supply energy which is equivalent to, this is very important condition. Your energy should be equivalent to E2 minus E1 should be equivalent to H nu. Nu is nothing but frequency. Okay, nu here is frequency and H is, yes, Planck's constant. This is very important. So this electron now goes from ground state to the exit state or state E1 to the E2, and it is basically goes here. So instead of mixing in the same figure, what we do is we will write before and after. Okay. So before, what happens? Before, this is not there. Let me write that. This figure is for before absorption. Electron is sitting there. But after absorption, where it went? After. If they ask you to write, you write before and after. After the absorption, the electron goes. Where is the electron? Here or there? In the E2. So put the electron here. Simple. There is no electron. It absorbed the energy and went to E2. Simple. Now, because we are dealing with the quantum mechanics, this is purely quantum mechanical. Quantum mechanics deals with the probability. What you are asking is, look, I supplied this much energy. What is the probability that the electron can go to the excited state? That you are asking. So you need to write the probabilities. The probability is where it is going, state 1 to state 2, right? P1, 2, 2. And is it what kind of emission absorption? Stimulated absorption. So write stimulated absorption, or else only absorption also fine. In some textbooks they write only absorption or stimulated. Absorption is nothing but stimulated absorption. Therefore, stimulated absorption is proportional to what? Observe here. Probability depends on what parameters? First, energy. Then only one person is there. You are giving 4,000. Sufficient. He went to Delhi. Suppose you gave 8,000. Only one person is there. Can two people go? Only one person is there. If you give 30,000, still one person is there. How many can go to Delhi? Only one. So if here so many people are there, so your money and also people, yes or no, matters a lot. Here not just energy, number of electrons also matters, yes or no? It's not just energy, probability depends on you're dumping a lot of energy, but you need to have enough number of candidates at the ground state. Yes or no? Therefore, your probability depends first on energy. Let us call some U. U is energy density. Okay, remember. It depends on energy density by default. Not only that, it also depends on number of electrons at the ground state. Yes? Let us combine it. If I combine it and write P of 1, 2 of absorption is proportional to U and N1. Let us take out the proportionality constant. P1 to absorption is equal, give some constant whatever you want. Let me give it is A, because I am going from state 1 to state 2. Let me write A1 2 and it is U N1. Up to here you need to write. If somebody is asking you to explain the process of stimulated absorption along with the theory, no need to by heart the theory. Simple lines, whatever you understand, put it in your own words. Use the terminology like energy density, stimulated absorption, such kind of things, photon energy, all these things. Anything is not clear here? Any doubts? Clear, right? All right. Then we'll go to the next section. Okay. Somehow it went to there, but now it cannot stay permanently there. So let us start where we stopped. Where we are? We are here. My electron is in the state E2. This is E2. This is E1. By the way, which has higher energy? Remember that your E2 is greater than E1. Keep it in mind. Now it is excited state. How much time we are in the excited state? You hear some good news, you will be excited, but for how long? Some time. Then you have to come to natural normal life. Same thing applies there. Okay? It takes the energy and goes, but it is not its originality. It's not stable state. It will eventually calm down. So look guys, it stays there very, very small time. No, the time is almost 10 to the power minus 8 seconds. And it too small. It stays there for very short period of time. Then it has to come back to its own position. So after 10 power minus 8 seconds, it cannot stay there. It will come back to, after 10 power 8 seconds, it wants to come back to its own position. So it will come back to energy E1. But remember one thing, while it is coming down, it will not come as it is, but it should release the extra energy it has taken. Got it? What is the energy? It is, if I call the energy is h nu, my h nu is equivalent to how much? E2 minus E1. Very good. Sit there, sit there. 9 o'clock will give. Yes. So this you have to say this process of emission. Why? You are emitting a photon. Emitting a photon. But is it happening naturally or unnaturally? Naturally it is happening. So we call it is spontaneous emission. Spontaneous emission. Next they will ask, explain about the spontaneous emission. Same thing. This is before the emission diagram and this is after the emission diagram. Please write it. Here, sit here, sit here. Don't come. Class is going, no? Right? Write the probability. Tell somebody, tell me the probability. Again, the probability of spontaneous emission. P, where it is coming from? 2 to 1. P, 2 to 1 it is. Spontaneous emission is proportional to, somebody tell me, spontaneous emission proportional to what? Look at the diagram and tell. Is the energy involved? Look there. Is energy is involved? Anybody is forcing? No U dependence, no energy density. What it depends on? Just number of electrons. How many are there on the top? How many are coming down? Yes. So it is purely depends on N. Hey, N2. N2 is nothing but number of electrons in the state E2. N1 is nothing but number of electrons in the state E1. Okay. So it purely depends on N2. Take out the proportionality constant. Then P21 of spontaneous emission is equal to, find A, 2 1. But in textbooks you will not see A. They will use B for some reason. So I will tell why it is. Let us use the same thing. B 2 1 N2. That's it. This is the probability. Any doubt here? How many number of photons released in the process of spontaneous emission? How many? Look there. How many number of photons released? For one transition, one photon. That's all. Keep it in mind. All right. So this is how light comes naturally, generally. You give electrical energy, electron takes, goes up, comes down. While coming down, the extra energy gained through the electricity, it is releasing in the form of photon. Tungsten filament you are taking, normally no energy because the electron cannot jump and come down. So you have to switch on electricity. Then the electron can take this electrical energy. So I call it is external energy. It takes, goes up, comes down, releases the light. That's how all our lights work. But laser is not that kind of light. What should happen? It should amplify it. Therefore, what Einstein thought is, well, this is natural process, but let me think differently. What happened is, here there is E2, electron is going from E1 to E2, yes, but it is staying how long? 10 power minus 8 seconds and coming down. Imagine if electron stays little bit longer, it is not coming down, it is waiting for somebody else. It is like, no, you also wait for your friend sometimes, no, we'll go, let my friend come, we both go together. Such kind of scenario. Electron stays little bit longer here. I say more than 10 power minus 8 second. Then because it is not going, what happens is I need to supply external photon, and now this external photon forces that guy because he is not going. Okay. Because I supplied external energy, now it will definitely try to come to the state T1. Naturally, it comes after 10 power minus 8 seconds. But for some reason, I will explain that why it is. It is not coming. It stays longer time. Then you are stimulating it or forcing it by supplying external energy. So by taking a stimuli is nothing but an agent. By taking a stimuli, the electron is coming down. Okay. Now what happens after coming down? It is taking the stimuli. Now the electron somehow comes down. Look here, it is coming from E2 to E1. Usually in the spontaneous emission or any emission, when the electrons comes from higher energy to the lower energy, what happens? Energy is released. So because it came from E to E1, it came. How it came? Stimuli. Because of the stimuli, somebody thrown him or else forced him to go, right? Because it came, one photon released. Yes, because it came from E2 to E1. Due to the transition from E2 to the E1, one external photon, one photon released. But look, there is another photon sitting there. Whatever you supplied, that also should come down. So another photon will also come down along with this, right? It is like you are on the 4th floor, somebody is going and pushing you and both of you are falling down. Okay. So by providing one photon, look, this is the beauty of this emission. By providing one photon, how many I got? 2. If I don't provide, only one is coming. By providing one photon, I got 2 photons. Okay, the emission happened from E2 to E1, but it is not natural emission. I need to stimulate it. Yes or no? So this is called stimulated emission. So main difference of stimulated emission to the spontaneous emission is what? In the stimulated emission, we are providing external stimuli or external photon. It can be photon or anything. Some stimuli you are providing. Easy case, provide a photon. External stimuli you are providing and you are getting 2 photons as output. But whereas in the case of spontaneous, only one. They will ask sometimes, give the differences between spontaneous emission and stimulated emission. So write the diagrams as usual. This is before the stimulated emission. This is after the stimulated emission. Each time you need to have both the diagrams. The differences are very clear. In one case you are providing stimuli, other case you are not providing stimuli. In stimulated emission, 2 photons released. In the spontaneous, only 1 photon released. In the spontaneous emission happens after 10 power minus 8 seconds, but stimulated emission happens nearly 10 power minus 5 seconds. More means not too much more, 10 power minus 5 roughly. Around 10 power minus 5 seconds stimulated happens. And stimulated emission, the beauty is because more number of photons are there, if these photons, you repeat the process, 2 becomes, now suppose now you take these 2, repeat the process, it becomes 4, take 4, repeat 8, repeat, you can amplify. Look, you are amplifying. Yes, so the stimulated emission is responsible for the amplification of the light, nothing but laser. So one more question. So which emission gives the laser light? Spontaneous or stimulated? Yes. Let us write the probability of stimulated emission. The probability, where it is coming from? 2 to 1. Through what process? Not spontaneous, stimulated emission. Now you tell me, proportional to what? The probability of stimulated emission. Proportional to, think here, first energy, because you need to supply energy. Yes, and number of electrons set N2. Yes, so let us take out the proportionality constant. We can write P21 of stimulated emission is, you take A21 of U and N2. This is the reason we omitted intentionally there. In the spontaneous emission, we wrote B. Here I wrote A. Okay. A21. Now how many we got? In the previous page, we got B21. Before that, for the stimulated absorption, A12. So A12, B21 and A21. All these are called Einstein coefficients because there are some constants. So A12 is for what? Einstein coefficient for absorption. Einstein coefficients. This is Einstein coefficient for stimulated absorption, or else in simple case absorption. Don't get confused. Whenever you hear absorption, it is stimulated absorption by default because absorption can never happen. You wait as long as you want. You cannot go up unless I provide external energy. Then B21 is Einstein coefficient for spontaneous emission. Then A21 is Einstein quotient for stimulated emission. Okay. Now, what Einstein proved theoretically, this is very important. What Einstein proved theoretically is, look, you are providing external energy, but always you are getting normal light only. You are not getting any laser, no, normal scenario. But theoretically, what he said is, the external energy you are supplied is used for what? For normal light. The electrical energy you are supplying is used for what? For the production of normal light. Which process is happening? Stimulated absorption, no? But what he said is, the stimulated absorption probability and stimulated emission probability is equal. That's what he proved. Look guys, you are using it always for the stimulated absorption, but this also possible. Stimulated emission also can happen with equal probability. And he said, if only if you can achieve this, you can get amplification of the light is possible. If you amplify, it will become powerful enough. We are calling that as laser. Right? But what is the condition? You need to achieve it. But theoretically, Einstein showed that it is possible. What is this? The stimulated absorption, the probability of stimulated absorption is equivalent to, this is very important point, remember it. Why laser comes, or the what Einstein quotient gives is probability of stimulated absorption is equivalent to stimulated emission. So it is engineering problem. Probability is same. It can happen. Probability means it can happen, but you need to make it to happen. That is engineering problem. Physicist says that, guys, it can work. How? That is engineering problem. You need to solve it. But we took almost 60-70 years to tackle this problem to produce. After the proposing, we took so long to get first laser. It is not so easy. Though theoretically it is possible, experimentally we could achieve very recently only. Right? So anything they can ask in the exam. Difference between spontaneous and stimulated emission, or else explain the process of all these three, 7 marks sometimes. Explain only one for 4 marks. Anything, but definite question, more or less. Okay. So this is very important concept. Then one more concept I will explain in next 10 minutes. Look, so stimulated emission is happening now. For that, where you need more number of photons for the stimulated emission? Energy level 1 or 2? Yes, no? So if you want the stimulated emission to happen, you need more number of photons at excited state. Excited state. But naturally, where the electrons wants to be? In the ground state. So what is natural? Let me draw. Natural is, if n1 is the number of electrons, natural is n1 is number of electrons in energy E1. So how many are there? N1, let me write for the argument's sake, 5 number of electrons are there. My N1 is 5. And if N2 is the number of electrons in E2, how many are there? Typically very less. For the argument's sake, let me write only 2. Why less there? Because you need to supply external energy, take it to the higher. So natural one is more number of electrons are there in N1. So more number of electrons are there in energy state E1, nothing but N1 is greater than, and E1 is less than E2. So this is the natural condition. But with this condition, stimulated emission is not possible. What you want? You want contrary, which means your ideal diagram should be how? What you want is, you want more number of electrons at E2 we want compared to the number of electrons at E1. This is what we want for stimulated emission. Yes or no? Agreed up to here? Ra, why are you looking there? You agree with this? Pay the attention. We have very less. We want this. So where is the population? Here. This is a population is nothing but number of electrons. Population is more in the ground state. But here population is less in the ground state, more in the excited. So population is reverse. Yes or no? That for the stimulated emission, what should happen? Population should be reverse or inverse. So this is a important concept. They asked you to explain population inversion. Population inversion. We need the condition called population inversion. You write in your own words. In normal scenario, this is the condition. Write what is N1, what is N2. But if by some means population inversion happens, this is inverted now, what happens now? N1 is, after the population inversion, what happened? After population inversion, your N1 is lesser than N2, but E1, hey, don't get confused, right? So now ask, what is the probability N2 by N1? No, you have to take Boltzmann distribution law. I'm not saying Boltzmann distribution gives how many number of electrons are sitting in given energy at a given temperature. That's a Boltzmann distribution gives. So directly I'm writing, if I take Boltzmann distribution law, N2 by N1 is nothing but e to the power minus of E2 minus E1 by KT. This is from Boltzmann distribution law. Okay. So now you have to look, if you want N2 is equal to N1, what is the temperature you need to play with? K is anyway constant, E1, E2s are the energies, they don't change. Only thing you need to play with N2 and N1. What do you want? You want N2 greater than N1 you want. So that happens at what temperature? That's only you need to look. Okay. So even at room temperature, remember the population inversion happens. Okay. Up to here, minimum thing you need to write. If you are asking, explain about the population inversion with the beautiful diagrams and the theory, you can manage, I guess. Okay. Read once the textbook, you can manage it. But this is important. The Boltzmann distribution law is important, and it happens even at room temperature also it can happen. Otherwise, you need to have negative temperatures. For N2 to N1 should happen, you need negative temperatures. So they say it is negative temperature coefficients. But okay, don't go into that details. But remember, even at room temperature, the population inversion is possible. But how is it possible? That is my idea. My worry. How can you make it to possible? I'll tell you one classical example. Where is the water usually? Under the ground. Yes, but you want to take it to the tank on the top. Yes or no? Is it going? It's going somehow. How? Motor. You are basically pumping the water from ground to. You need to do the same thing. So our next question is pumping. How can you pump? Why do you want to pump? Era, why do you want to pump? ఉన్నావు ఎక్కడే ఉన్నావా? ఇన్నారా రే, గుండు పగిలిది నా లైట్ వాళ్ళకి. ఉన్నావు ఇక్కడే. ఎందుకు పంపు చేయాలనుకుంటున్నావు చెప్పు? వాటర్ కాదు, ఇక్కడ ఎలక్ట్రాన్ ఎందుకు పైకి తీసుకెళ్ళాలి? ఎందుకు? Why do you want to pump? No one knows. So you're not understanding anything. Why do you want to pump? To achieve the population inversion. Why do you need to achieve population inversion? For getting stimulated emission. Don't miss the connection. అటు ఇటు ఆలోచించమంటే తలగా పగిలింది. ఎక్కడుండు ఫోకస్డ్గా. సో పంపింగ్ మెకానిజం. How can you pump? Pumping mechanism. So next question, explain about pumping. Simple thing ra, laser is very easy. Everything is straightforward. So how can you pump? Imagine, how can you take the electron from ground to up? Simple. Everything you know. So pumping can be done by providing external energy. This term external is very important because internally already electron has specific energies. Okay, you need to provide from outside. So what kind of external energies are there? What kind of external energies you can provide? Name? Photons, huh? So that is called optical or light energy you are giving, or else optical energy. So fine, you take, no problem. Optical energy I can give. Write a para on that. Put a heading. What kind of optical energies you can give? Laser or some photon from outside. No, read the book, more details will be there. One is optical energy. Then what more you can give? Electrical energy. Very good. You can provide electrical energy. Then yeah, thermal energy. Nice. See, you know everything. What else? What else? What more you can give? In the textbook you read something called direct conversion. Direct conversion. Concept is clear. Due to the lack of time, not going into the detail of each one, but nothing more. Now basically you are giving different kinds of energy. How you are giving? Read a para from the book, you can understand. Okay, but pumping means you are achieving population inversion by supplying the external energy. It can be done in several ways. Those ways are given here. Write two lines for each way. That's it. You'll get full marks. Easy, right? So the next question they may ask, explain about pumping. You can also write. The final question is here, metastable state. Metastable state. This is very much important, but it is also very easy. Metastable state. Metastable state is nothing but, look, for the spontaneous emission, after how much time it is coming down? 10 power minus 8 seconds. Yes, but for stimulated emission it has to stay greater than, means typically how much I told? 10 power minus 5. Remember, some 3 into 10 power minus 5 10 textbooks may give, or 4 into 5 into 10 power minus 5, but in the order of 10 power minus 5 seconds. So but as long as your energy is like this is my ground state energy. Even if this is my excited state, some energy E3 or E4 something, let me write excited state, and this is ground state. Okay, let me start E1, E2, 1. If electron goes there, it has to stay only 10 power minus 8. After that, it has to come down. But you want more. Therefore, what happens is, look, this is very important point. What happens is, but you want stimulated emission to happen, do some engineering, do something, but don't let the electron come down. If it comes down, gone case, normal light only come. So before electron goes to here and it wants to come down, before it comes down, you say that introduce another energy level and trap it there for some time. Okay. So first electron was here. From here, due to the absorption, it goes to there. Yes, it was here, but instead of coming here, it goes to another energy level in between. So let me call this is E1 and the top one E2. This is E2, E1, E2. Right? Now ask, what is the lifetime of this guy here? It is greater than, more or less, 10 power minus seconds. But here lifetime is 10 power minus 8 seconds. Now this energy state E2, it is more or less stable compared to E3. Yes or no? More or less. It is not stable. Stable is E1 is stable state energy. This is not at all stable, but this is somewhat comparatively. So you call it is meta stable. Meta means it's not stable, but appears to be stable compared to the previous one. Yes. So E2 is called meta stable state. E2 is our meta stable state. Why do we need meta stable state? Our aim is only one. What are we looking for? Stimulated emission. So population inversion should happen now. Where should it happen? E2 or E3? E2. Right, one more point you got. So what happens in the metastable state? Population inversion happens there. Happens at metastable state. What is? So now from here to here electron is going, but you may ask, if you are smart, look, it is spontaneous emission kind, no? It is looking like spontaneous emission. You can ask. So if it comes from E3 to E2, does any photon release? You have to ask. Does any photon release? Technically it should release because it is jumping. It should release. But here it will not release. Instead, then you can ask, then what happens to the difference of the energy E3 minus C2? Some energy difference is there. Where does it go? It will transferred as vibrations of the atoms, but no photon will come out. Look here. So we call E3 to E2, no photon comes, so it is non-radiative transition between E3 to E2, which means electron comes from E3 to E2, but you are not seeing any light, any kind of light, because it is not radiative. The energy will be transferred as vibrational energy simply. Now at E2, population inversion is happening, then you are supplying external energy. From here to here, what kind of emission this is? Spontaneous emission. From here to here it is stimulated absorption. Now population inversion happens here and you are supplying external photon. Then what happens? This comes from there to here through the process called stimulated emission. Result of that will be, you will get 2 photons if you can supply 1 photon. Yes. Clear? So if laser is coming, under what transition it is coming? Where to where laser is coming? Oh, time is over, no? I'll close it. Over. So from E2 to E1, what is happening? Stimulated emission. This is responsible for lasers. All right. So I'll stop it here. Time is up. So up to here, can you write? Population inversion, metastable state. Read once, it is very easy. After that, essay questions, two only we have: NDYAG and semiconductor. NDYAG and semiconductor. Read it. One of them will come. How many energy levels are involved here? E1, E2, E3. So this is called 3-level laser. Sometimes 4 energy levels will come. 4-level laser. In NDYAG, these energy level diagrams are there. They are very important. If you don't write that, if they are asking, you will not get marks. Okay? So these energy level diagrams are important for the NDYAG. All right, let us stop. Please go. Stop that also.